Okay, good morning. Today we're going to take a look at graphing inequalities. Now, you should have some experience with this from when you're in Algebra 1, where you graphed linear inequalities. Now, I'm going to look at an example here. It says y is less than or equal to negative 2x plus 3. Now, what is the graph of it? What does a graph of a linear inequality look like? Well, let's first start by graphing the equation y equals negative 2x plus 3. Well, we know our y-intercept is this value right there, 0, 3, and we know the slope of our line is negative 2, which is a fraction of negative 2 over 1. Now, from geometry and algebra, we know that to graph any line, we need at least 2 points on the line. So what I'm going to do is I'm going to come in and I'm going to graph the y-intercept, 0, 3, right here. And now I need a second point. Well, the slope tells me to go down 2 and right 1. And I can repeat that if I want. Or I could go up 2 and left 1. Yeah. And you just connect these points with your line. Right? Now, what is the purpose of an equation and a graph? Well, remember that the whole purpose of this line, it represents all the solutions that would be all the solutions to this equation right there, right? Like for example, if I plugged in, say, 1, 1 into x and y in this equation, you would get 1 equals 1, so that works. If I plugged in, say, negative 1, negative 1, 5 into this equation, if I plug a negative 1 in for x and a 5 in for y, I would get 5 equals 5, right? So again, the purpose of the graph, of any graph, is to show you the points that are on the graph that will satisfy or be solutions to his related equation. Now, with an inequality, let's take a look at what's happening. I still want to draw a graph to represent these two variables, x and y. And I'm still going to graph the related line, y equals negative 2x plus 3, like I did in the previous problem. Have a y-intercept of 2, go down 2, right 1, down 2, right 1, or up 2, left 1. And I still want to draw a line connecting those points, right? Now, because of this equal to sign, would you agree? Well, every point that's on the line will satisfy this inequality because of the equal to. It's kind of like a mixture between an inequality and an equation. So I'm still going to draw that line connecting those points, and that line will be a solid line, correct? So that every point on that line will be a solution to this inequality because of the equal to sign. But now what I need to do is I need to graph other points as well. I want to graph points that satisfy the inequality part, the less than negative 2x plus 3. Well, at this point, probably what you learned was to pick a test value. And probably the most popular test value that you picked was the origin 0, 0, just because doing math with 0 and 0 is really easy, right? So if I plug 0 and 0 into this inequality, I would get 0 is less than or equal to negative 2 times 0 plus 3. So 0 is less than or equal to, well, if you do the math on that right side, wouldn't you get 3? Now, again, we want a point, which was 0, 0, that makes this inequality true or satisfies the inequality. Well, you ask yourself, is 0 less than 3? Yeah, that's true. So this point, 0, 0, is a true point. Well, the nice thing is, if one point on this side of the line is true, every point on that side of the line will be true. And so what ends up happening is you get a graph that looks like this. You would shade in this side of the line because there's so many points that would work. If I tried to make every individual point that worked, I would get just a solid shaded region. And that's what we do. We can take a test point. Now, we're going to do the same thing, but instead of just doing lines like you did in Algebra 1, we're going to look at using parabolas and absolute values as well. Okay, so to graph this next problem, if we take a look at this, I've got a quadratic. Now, we talked about this earlier. A quadratic, the graph of that is called a parabola. But instead of just graphing what looks to be a U or an upside down U, we're now going to graph a U or an upside down U, but we're also going to have to shade. So to do this, I know that we can only graph a parabola if we change it to vertex form using completing the square and then look at the transformations. So I'm going to take the first, I'm going to take the related equation, 2x squared minus 4x plus 1. Remember, to complete the square, I first move the 1 across. And I'm allowed to complete the square if I have a number other than 1 in front of the x squared, so I have to factor out whatever that number is. And then I know I want to add in my own number to both sides. Now again, the purpose of completing the square, go from 2 variables down to 1 variable, so I need to go from 2x's down to 1x's. We take half of -2, which is -1. We square that. We're going to add a 1 to this side. Now again, as a review, if I add a 1 into that parentheses, I'm actually adding 2 to that right side. So I have to add 2 to this left side. So what I get is y plus 1 equals 2, and now I can factor that parentheses into x minus 1 squared. Now all I do is isolate y by subtracting the 1 across, and I get y equals 2x minus 1 squared plus 1. So now I can look at the graph of this from the parent function. I know I've got an xy table for y equals x squared, where I like to plug in -2, -1, 0, 1, and 2. The y values, when I plug in -2, -1, 0, 1, and 2 into y equals x squared, would be 4, 1, 0, 1, and 4. Right? Don't forget that's my parent function for a parabola. Now, what are the transformations? I've got adding 1 to all the x's from the h values. So if I add 1, I get -1, 0, 1, 2, and 3. And then my y values, I've got 2 transformations. I've got to first multiply all the y values by 2 for my a. So I get 8, 2, 0, 2, and 8. And then I have to add 1 to all those. So I get, adding 1 to all my y values, 9, 3, 1, 3, and 9. So from there, my table of values is going to be -1, 0, 1, 2, and 3. And my y values are going to be 9, 3, 1, 3, and 9. So graphing these out, left 1 up 9, left 0 and up 3, up right 1 up 1, right 2 up 3, and right 3 and up 9. So I get a parabola that would connect these points. I get a U. Now here's the next thing. Remember how we said with an equation we would graph a curve that would satisfy that its points would satisfy this equation? Well, I'm graphing an inequality that has no equal to sign. So even though I need to graph a parabola, I'm going to graph this using a dashed curve. You guys remember that from Algebra 1? Meaning this will divide my graph into points that work for the inequality and points that don't work, but the parabola itself will not satisfy this inequality because there's no equal to sign. Okay, so now let's pick a test point. So I'm going to pick 0, 0 again, because as long as it's not on the graph itself, I can use it. Plugging that in to the inequality, let's see if I get a true statement or not. I get y, or I'm plugging in 0, 0, sorry. 0 is less than 2 times 0 squared minus 4 times 0 plus 1. So I get 0 is less than 1. Well, is 0 less than 1? Well, that's true, by golly. So since 0, 0 creates a true statement from this inequality, I know that this point works. Well, again, for a parabola, unlike a line, a parabola is more like, instead of shading above or below the line, I'm going to shade either inside or outside the parabola. Since this point was true, I know every point on the outside of the parabola will be true, and my graph would look like that. So if you think about it, graphing inequalities, what's the only difference between graphing an inequality and the equation? Well, you're still going to graph the equation. You're still going to graph the equation, but you're going to have more work to do. You're going to have to shade one side of the graph or the other, okay? And so you're either going to graph for a parabola, either the inside or the outside, all right? But you're going to graph the inequality just like you graph an equation. Okay, let's look at one more inequality. We've graphed absolute values. Now, we said there was a shortcut for graphing absolute values, and that shortcut would say, I know I have a vertex, and the vertex in this case would be -1, 5. I know that my slope, because it's just 2 lines, would be -2/3. Well, to graph an absolute value, I would go left 1, up 5, 1, 2, 3, 4, 5. And from here, I go down 2 and right 1, 2, 3, and down 2 and left 1, 2, 3, because of the symmetry. And then you would graph your 2 lines. Now, to make your V. Now, again, we knew this was going to be upside down because of that negative sign right there. So when I graph my upside down V, I'm going to use a dashed line to draw this. 2 dashed lines like that. Okay? And now that I've graphed my border graph, I need to find out which points would satisfy the inequality of y is greater than -2/3 x plus 1 plus 5. Now, if you think about it, there's actually a shorter way other than picking a test point. Maybe you can come up with a conjecture on how you can decide the shading other than the test point. Again, I'm going to pick 0, 0 as my test point, plugging 0 and 0 into the absolute value inequality. I get 0 is greater than -2/3. Absolute value of 0 plus 1 plus 5. So I get 0 is greater than -2/3 times the absolute value of 1 plus 5. So I get 0 is greater than, well, the absolute value of 1 is just 1 plus 5. So I get 0 is greater than -2/3 plus 5. And 5 minus 2/3 is 4 1/3. So is 0 greater than 4 1/3? Well, in this case, that's false. 0 is not greater than 4 1/3. So since this is a false point, I know that everything inside the absolute value, all these points would be false points. And the true points would be the points that are outside on top of that absolute value. And so that's what your graph would look like. All right, folks. I'll see you in class tomorrow.